So statics, okay? So statics, as the word says, is when a fluid is at rest, so there's no acceleration to the fluid. A static fluid doesn't have any shear force acting on it, right? So there's only normal forces acting on the fluid, otherwise with the shear stress there will be a deformation of the fluid and an acceleration of the fluid. So the only force acting on the fluid are normal, and that's pressure. Okay? So any force between fluid and boundary must be acting at right angles and normal to it. And a fluid at rest is in equilibrium because it's not accelerating. So the sum of all the components of the forces in any direction must be equal to 0. So in all the components in x, y, z, in a Cartesian framework, all the components of the forces must be equal to 0. Okay? That's an example of hopefully a static fluid. Okay, so in a static fluid, the only force acting on the fluid is in the normal direction, and that is pressure. Okay. And so we're gonna make a very simple example of the isotropy of pressure. To then derive what we call hydrostasy, okay, which is something that perhaps you've seen already in, well, maybe not, well, in physics of the atmosphere. I guess you've seen hydrostasy already, maybe not. Okay, so this is where it's coming from. Okay. So pressure is normal, is a normal force, okay, per unit area. So we have pressure, which is a normal force in a static fluid per unit area. Okay, that's the only force acting on the fluid. So if we consider an infinitesimal point, okay, how does pressure vary with the orientation of the plane? So we can have a simple example of this kind of shape, where we have some delta x, this is going to be a delta z, and it's unity in delta y into the board. Okay, so in a static conditions, all forces in all directions must be equal to 0. Okay, so there's no acceleration. And so how does pressure vary in this infinitesimal volume of fluid? We have here a Pz, which is dx and y. We have here a P, this is x, dy and z. Okay. And then we have here a P called S, dy and ds on this delta S of this infinitesimal volume of fluid. And this is my angle theta. Okay, then there's something else acting on this infinitesimal volume of fluid, which is its own weight. We're going to make the assumption that it's infinitesimally small, so weight is going to be infinitesimally small, but nevertheless, we can start with the general case of a delta x, delta y, delta z over 2, where I have defined rho as density and gamma to be the specific weight. Okay, so in a static condition, all the forces in all directions must be equal to 0, or must cancel out. So just remember that here, delta x is delta s cosine of the angle theta, and delta z is delta s, the sine of theta. Okay? So, to start from the general case, we're going to use Newton's second law. All the forces equal to some mass times the acceleration. It's going to be static, so acceleration will be 0. And so all the components of the forces must be equal will cancel out in every direction. Okay? So the sum of all the forces in X are going to be Px dy dz minus the contribution from Ps dy ds sine of theta, okay, equal to whatever mass times acceleration I have, and in z I will have pz dx dy minus my contribution dy ds cosine of theta equal to my mass times the acceleration. Okay, so this is dz, okay, cosine theta, and this is dx, okay. So this is equal to px minus ps, and this is equal to pz minus ps. Equal to my rho is equal to some acceleration, and rho a component plus my gamma 0,2. Okay, so if you just make the assumption that this is an infinitesimally small element of fluid where delta x, delta y, and delta z are very small, if delta x, delta y, and delta z are very small, then delta x, the volume delta x, delta y, and delta z is going to be extremely small. So you can make the assumption that as delta x, delta y, and delta z are going to 0, as we're interested in a single point, then trivially this just reduces for an infinitesimally small element of fluid to all the components in the pressure being equal, px, py, and pz. Okay? So all the components of these forces are equal in all directions. So this is true as long as there are no shearing stresses on the surface of the element. Okay? Now this is pretty obvious. Okay? And so this is what is called the isotropy of pressure. So in a fluid at rest, so no shear stresses, the tangential viscous stresses are absent, okay, they're 0, and so the only force is normal to the surface, which is the pressure. And the surface force per unit area, which is the pressure, is equal in all directions, just by definition. So the fact that the pressure at any point in a fluid at rest has the same value, then it reduces to a scalar. Okay? And this is just called the Pascal's law. So in a fluid at rest, every point has the same value of pressure. Okay? And that's called the Pascal's law, which is used, we will see an example, is used in many engineering applications. Okay? So what happens to pressure in a fluid? Okay, we're now going to consider an infinitesimally small element of fluid anymore. So we're going to consider, bless you, a small element of fluid now. Okay, and in this small element of fluid, there are going to be two forces acting on fluid. going to be a surface force, and the surface force is going to be pressure, and it's going to be a body force. We will define surface forces and body forces, I think, next time, but it's pretty intuitive. Surface force is pressure acting on the surface of the element of fluid, and the body force is, of course, gravity acting on the element of fluid. Okay, so we can define this small element of fluid. Okay, so no shear stresses acting on the element of fluid, just a surface force, which is pressure, and a body force, which is gravity, or its own weight. Okay, so what are the forces acting on this element of fluid? This is the center of the element. So we have the pressure plus the dt by dx delta x over 2 y and z, and here we have p minus dp by dx dx over 2 y and z. Okay, so just do a Taylor expansion to approximate the value at the boundary with respect to the center. Okay. Here at the top, what do we have? We have pressure plus dp by dz equals 2 dx and dy, and so on and so forth in all phases of the element of fluid. Okay, here we have p minus dp by dz equals 2 dx and dy. Okay. So the element is in equilibrium, so imagine an element of fluid, a particle of fluid, a droplet, or an element of air in the atmosphere, which is in equilibrium. It's not accelerating, it's not moving. Okay. So this means that all the acting forces must be equal to 0 on the element of the fluid. Okay. So in the x direction, what are the forces that we have? If you just do this minus this, you have dp by dx, dy by z, and in y d by dy, and the z component, of course, we have dx, dy, and z. Okay? It's just doing one plus the other in all of the different directions. So all the forces okay, so these are your pressure components, which is just dp by dx minus dp by dy minus dp by dz in the k direction, dx, dy, and dz. Okay. So the forces per unit volume, so this is my volume of this small element of fluid. So the surface forces per unit volume are going to be my pressure gradients. Okay, obviously. But that's not the only forces acting on the element of fluid. There's also a body force acting on the element of fluid, right? Which is its own weight. So if we define the weight by,
excuse me.
yep.
Excuse me for this. I'm trying to understand how you're deriving the different components, because from this formula, for example, taking f of x equals minus dp dx, then small changes across the various like component x, y, and z. So if that is dx, then
Sorry, how do you get to this?
the pressures in the different, all the pressures.
Yeah, so this is my delta x, and this is my delta y, and this is my delta z. Okay. So with respect to the center of the element fluid, I have the pressure plus this. So you just do a Taylor expansion on the center of the element. But so if here you have pressure, here on the face of the element you have pressure plus any variation in pressure on x dx over 2, because this is dx over 2. Okay. And here you have the same pressure minus dp by dx over this delta x over 2. Okay. So on the face, this is the pressure that you have. Here you have p. Here you have p plus dp by dx over this delta x2. Okay. So here you have a plus, and here you have a minus. Here you have a plus, and here you have a minus, and the same thing there. When you consider all the forces in the x direction, it's going to be this minus this, so p goes away, minus dp by dx, minus dp by dx, times delta x, because now you're summing these two halves. So you're just left with minus dp by dx, and minus dp by dy, and minus dp by dz. So all the surface forces acting on the element of fluid is just the gradient of the pressure. But then you have the weight, okay? So it's not an infinitesimal element of fluid anymore where you can just disregard the volume. You have a weight, and so you define the weight as the specific weight again. Okay, it's in gamma, which is directed in the down. Okay, so if we use again the Newton's second law, so we have the sum of all the forces is equal to my delta m acceleration. This is my element of fluid. Delta m is just rho dx, dy, and z. Okay, so I have that my surface forces minus my weight is going to be equal to my element of fluid, the mass of the element of fluid times the acceleration. It's not going to be an acceleration force. So this is minus rho p, okay, my forces, dx, dy, dz. Then I have minus gamma, dx, dy, and z. This is my weight. Okay, so these are the total forces acting on the element of fluid times rho dx, dy, dz, and acceleration. Okay, so you just get rid of the volume. Okay, and of course, as we started off by saying that there is no acceleration because the element of fluid is at rest, A is equal to 0. Okay. So what do we have? We have that rho p is equal to minus gamma. Okay. Yeah. But what is gamma? Gamma is the specific weight, okay, and the specific weight is only one direction, so gamma is gamma only in the vertical direction. Right. So that means that in the horizontal direction, in x and y, my dp by dx must be equal to dp by dy, which are equal to 0. That's the in the horizontal direction, because the fluid is at rest. All the forces and all the different components must compensate each other and be equal to 0. And then we are left with dp by dz is equal to minus rho g, which is my gamma. Gamma is the specific weight. Okay, so in the horizontal, so the fluid is at rest, so there must be a force balance between in all the different directions, in the x direction, in the y direction, and in the z direction. So in the x and in the y direction is similar to the infinitesimal element of fluid. There's the only forces acting is the pressure, so all the forces acting in the x direction, the pressure must be equal to 0. All the components in the y direction must be equal to 0. Okay? So all my dp by dx, dp by dy must be equal to 0 because there is no other force. In the vertical now we have a weight. Okay? So my dp by dz, my variations in pressure in the vertical, they balance the weight, okay, which only has the vertical component. Okay? That was my rho g per unit volume. Okay. So if you don't want to move, in the horizontal is pretty easy. If you're an element of fluid, liquid, a gas, whatever, okay, in order to be at rest, there must be a balance. In the horizontal component it's trivial. In the vertical component there is a balance between your pressure variation in the vertical and rho g, which is gravitational, the body force, okay? Because you're not moving, so these two are the only forces acting on the element of fluid. And this is a very important, although very simple, is a very important force balance in fluids and in geophysical fluids, which is called hydrostacy. Okay? Or you might be more familiar with just the hydrostatic balance. Okay? So whenever you do geophysical fluid dynamics, you'll be talking about hydrostatic balance a lot. Okay? And you'll see this in physics of the atmosphere, physics of the ocean, ocean dynamics, geophysical fluid dynamics, so on and so forth. Okay? So this is called the hydrostatic balance. Okay? So any variation in pressure in the vertical is balanced by the gravitational force, or the gravitational force is balanced by pressure variations in the vertical. Okay, a more elegant way of reducing hydrostacy faster way and definitely more elegant. So there is a balance, okay? We said there is a balance between body forces balancing surface forces. Okay, and the only surface force is pressure in static conditions. Okay? So imagine an element of fluid which has this potato shape, something like that. Okay. On the surface we have this element of the surface dA, and pressure has a magnitude and a direction, P dA. Okay. And there's a weight acting on this element of fluid, so now that's my volume, which is rho g dV. Okay. So this will be my body force, and this will be my surface force, my pressure. Okay. You could just generalize this as we'll say this. So this is my body force, F, okay, and this is my surface force, pressure. It's going to be called, any body force is going to be called F, okay. And then when you enter geophysical fluids, there will be one body force, gravitation, and a second body force, which is Coriolis. Okay, that's another body force. It's not a surface force, it's a body force. So for the entire volume, this body force is my body force integrated over the entire volume, and my surface force integrated over the entire surface is just the pressure integrated over the whole area bounding my volume. Okay, so in static conditions, these two have to balance each other. Okay, so in static conditions, the two have to balance each other. And now here what we're going to do is use the Gauss theorem, which I will explain in 15 minutes. Okay, so the Gauss theorem relates an area integral with a volume integral. Okay, so I'm going to use the Gauss theorem on this area integral, and the area integral of pressure is equal to the volume integral of the divergence of pressure, or the gradient of pressure, because pressure is a scalar. Okay? So by using the Gauss theorem, I go from an area integral to a volume integral. So now this is going to be equal to this in static conditions. Okay. Is equal to 0. Okay. And so my graph P is equal to rho f. In my f, we said that f is minus rho g. So again, dp by dz is minus rho g. So this is a much simpler way of deriving the hydrostatic balance. Okay, so something extremely simple, but you'll use hydrostatic balance in every geophysical fluid that you're going to look at. Okay? And it's something very useful. So if you're a modeler, or if you're going to become a modeler, unless you use models of extremely high horizontal and vertical resolutions, you will make the assumption of hydrostatic balance. So this is one of the equations that enter our big models. Okay, very simple but very powerful. Okay, so that's the Gauss theorem that we just used. We're going from an area integral of a vector field to the volume integral of the divergence of the same vector field. Okay, so that makes sense. There's another theorem that we use a lot. So the outward flux. So if this is your volume, the outward flux of your vector field could be velocity vector, for example. Okay, that is equal to the divergence of the velocity vector within the volume. Okay? So if you have sources and sinks of anything in your fluid, okay, so that's the divergence within the volume of integration. You have sources and sinks into and out of the volume. Then the net effect will be the outward flux of your vector through the boundary bound on the volume.
Excuse me, Professor. From that doesn't seem to hold. F then must be equal to G, not rho G.
Is that? Sure. Thank you. No. Yes. Okay, the body force is the gravitational force. Okay. The body force is the gravitational force. And in a physical fluid, you have the gravitational force plus another force, which is Coriolis. Okay, so hydrostatic balance, simple, derived from static conditions, so there are no acceleration, there are no shear stresses acting on the fluid. So there's a balance between surface force, which is just pressure, and the body force, which is just the gravitational force. So how is this used? Let's think of incompressible fluid. Okay, so for an incompressible fluid, my gamma rho g is a constant and is a good, yeah.
Will there be gradient or divergence?
Yeah.
What? Where?
Okay, Gauss theorem, when you use Gauss theorem, when you go from area integral to volume, then it will be divergence, yeah?
What it? So the divergence theorem is, so the generalized version is the Gauss theorem. Okay? If you have a vector, then it's a divergence. If you have a scalar, is grad p. Okay? So if this is velocity, you have a vector, then you have a divergence. If you have pressure, you just have grad p. Okay, so thinking of this as constant, it is a good approximation in liquids. Liquids are not really incompressible, but it's a good approximation. Okay. So I have my hydrostatic balance. Okay. And now I can integrate this from P1 to P2. This is my gamma from Z1, Z2, whatever height or depth you want to think of. Okay, so this is just P2 minus P1, which is equal to minus gamma Z minus Z2 minus Z1. Now you make you need a reference level. Okay, so we call P1 my P0, which is my atmospheric pressure. Okay, so that's my reference level. So P minus P0 is equal to minus gamma Z minus Z0. Okay, I'm just taking a reference level, which is my pressure at the surface, which is my atmospheric pressure. So my pressure is going to be gamma H, where H is Z minus Z0. Okay? Z minus Z0 is negative because think of a fluid, okay? That Z, which is negative. Okay, so H is negative. So the pressure is just gamma H, starting from the other side of balance. So H, because of H, this is called the pressure head. Okay, and P is my gauge pressure, which is what you normally measure. Reference to a reference level, which is the atmospheric pressure. Okay. Now for compressible fluids, so this is good for liquids, for example, if you think of the ocean. If you're thinking of the atmosphere, then you have to look at compressible fluids. Okay, so now gamma is not going to be a constant anymore. So air is a function of pressure. The density of air is a function of pressure, is highly a function of pressure. Okay, so now we start again with the hydrostatic balance. Minus G, which is minus P RT G. using the perfect gas. I guess you've seen this, right? The perfect gas. Perfect gas is just P equal rho RT. Okay. And you start substituting things and then separating variables. P1, P2, PP minus GR, Z1, Z2, dT over T. Okay. ln of P2, P1 minus G P2 of ZT. Okay. So now you can go on from here, or you can make the assumption of constant temperature. Okay, so we assume temperature is constant, some T naught, and this is actually useful. Okay. And so if that is the case, then you have minus G R your T naught Z2 minus Z1, okay, which is P2 equal P1 this and this is something again very useful, which is called the pressure elevation relationship for an isotherm. Okay, so an isotherm, you consider part of the fluid which has constant temperature. Okay, so you're looking at the isotherm in the atmosphere, or you're looking at the isotherm in the ocean, and you look at the pressure elevation relationship. Of the isotherm. Okay. And this is probably something again that you've seen or you will see in physics of the atmosphere. Okay. And this is all, so it's all very simple, but it's something that we use every day in our models and in our theories. Okay, hydrostatic balance, gauge pressure, and the pressure elevation relationship for an isotherm. So now you can define all your different pressures. So you have an absolute pressure, which is your gamma H plus the atmospheric pressure, or GH. Okay, and that's how you define your absolute and gauge pressure. Okay, so if you take a reference level of the atmospheric pressure, for example, okay, your gauge pressure, which is this, is just given by gamma H. Okay, whatever difference you have from the atmospheric pressure, which is this. Okay, so the atmospheric pressure plus the gauge pressure is giving you the absolute pressure. So usually we talk about, whenever we say pressure, we talk about gauge pressure. Okay, so atmospheric pressure is usually called barometric pressure. It's what you measure reference to the atmosphere. Sorry, the atmospheric pressure is called the barometric pressure, and the units is 10 to the 5 Pascal or 1 bar. Absolute pressure is really not that much used, especially in geophysical fluids. That's a typical variation of pressure in the atmosphere. And okay, Pascal law. A funny example of the Pascal law. Do you remember the Pascal law in a static fluid says that all points are feeling the same pressure, and the pressure is the same. So if you're an engineer, you have probably thought about this problem a lot. And also in your everyday life, you've probably used Pascal law without realizing it. So imagine this system, okay, this is filled with a liquid, where rho is a constant, okay? And you apply a force F1 to this area A1, okay? And this area is A2, where A2 is bigger than A1. Okay, so at the same depth, we have a pressure 1 and a pressure P2. And in starting conditions, this P1 must be equal to P2. Density is constant, very starting conditions. Pressure is still the same. So pressure is a force per unit area, so we have F1 A1 equals to F2 A2. Okay? But A1 is larger than A2, is larger than 1, so this means that F2 must be larger than F1. F2 is A2 over 1 F1. Okay, so because of Pascal law in static conditions, the pressure is the same at the same depth. Okay, if I apply a force F1 over an area A1, which is equal to my pressure 1, pressure 2 must be equal to pressure 1. Okay, and pressure 2 is nothing but F2 per unit area A2. Okay? So this means that if you push, or if you apply a force on this side of this system, in order to maintain the pressure equal at all levels, you will generate a force per unit area in order to give you the same pressure P2 equal to P1. And the forcing resulting from this equilibrium of the Pascal law, F2, is much larger than F1 because A2 is larger than A1. Okay? And this is called the multiplication of forces. Okay? So and there's a very simple example of this. So think about work. You have work which is equal to F times some distance D. Okay, that's my work. And so the work that I do F1 D1 must be equal to my work F2 D2. So my D1 is equal to F2 over F1 D2, which is equal to A2 A1 D2. Okay? But I know that A2 is much larger than A1, meaning that D1 must be much larger than D2. Yes. How does this translate to applications? So remember, we have this system filled with a liquid or a fluid of the same density. In static conditions, P1 has to be equal to P2. I apply a force F1 over an area A1. In order to maintain the same pressure, I have to generate a force that per unit area gives me this pressure. Okay? And the result is that because A2 is much larger than A1, F2 is going to be much larger than the original force. Okay? So if I apply a force here, there will be a force on the other side of this element, which is much larger than the one that I applied. And in terms of work, F1 D1 must be equal to F2 D2, okay? But F2 is much larger than F1, so that D1 is going to be much larger than D2 in order to maintain balance, okay? What does that mean? Take an example, an everyday example is this, well, this is what I've written, the hydraulic lift, okay? This is an engineering example of applying the Pascal law. So whenever you go to your mechanic to change your tires, the mechanic is using Pascal law, okay? Because you're putting the car somewhere on a plate, which is A2, okay? And the mechanic is pushing a button and is pushing a liquid, which is applying a force on a tube, okay? And that tube, which is very long, D1 has to be very long, is generating within the liquid, pressure has to be the same. And so eventually on the other side, wherever you have left your car, there will be a resultant force that is much larger than the one that you applied, okay? So to lift a car that is 6,000 Newton, you need a force that is 15 Newton, okay? The problem is that you need a small force here to generate a large force here that will lift your car. Okay, fine, that's easy. But the problem in terms of work is that D1 has to be very long. So if you have ever visited a mechanic, you know that below the car there's actually a very long cable filled with the liquid. Okay, and that long cable is D1. Okay. So D1 has to be very long where you apply the force in order to get an F2 that is able to lift your car. This is a simple example, but you see Pascal law applications in geophysical fluids as well. Okay, so a small force, a stress or something that is applied on one side of your element of fluid, okay, results in a force somewhere else which is much larger. Okay, talking again about the hydrostatic balance. There is another application of the hydrostatic balance, which is the buoyancy force. Okay. Again, talking about geophysical fluids, you see buoyancy force everywhere. Okay. So pressure in the atmosphere decreases with height. Okay, that's the red line going up. And so the pressure force on the balloon, you have your pressure going this way with height. Okay. So this is your pressure decreasing with height, and imagine you have an element of fluid, for example a balloon, okay? So the pressure felt at the top is going to be smaller, the pressure at the top is smaller than pressure at the bottom, okay? And so the resultant, the difference between the two is the buoyancy force, okay? And that's why the buoyancy force is always directed upwards. Okay, because pressure at the bottom is larger than pressure at the top. So the buoyancy force is trying to lift you up. Okay, so the buoyancy force is always positive in the upward direction. If you're in the ocean, it's the same thing. This is Z going down deep into the ocean. You have your element of fluid, and again, your pressure at the bottom is larger than your pressure at the top, and it's trying to lift you up. Okay, so any element of fluid is experiencing a buoyancy force which is directed upwards and trying to lift or move the particle or the element of fluid in the upward direction. Okay, so that's the buoyancy force. Buoyancy force is a force exerted by a fluid that opposes an object's weight. Okay, so imagine this balloon or element of fluid is actually immersed in a fluid, which is what the balloon is immersed in a fluid, which is the atmosphere, right? And so that little grey ball is totally immersed in a fluid, or you might think of something floating on the ocean, okay, which is not totally immersed. So the force is equal to the weight of the fluid displaced, not the weight of the element, okay? So the force is equal to the weight of the fluid displaced by the object. So the buoyancy force is equal to the density of the fluid, not the object, so the ambient fluid, times gravity, times the volume displaced. Okay? So that ball is displacing this much of fluid, Okay, so the buoyancy force that this ball is experiencing is the amount of this volume displaced by the ball times gravity times the density of the fluid, not the density of the object. Okay, if the object is totally immersed in a fluid like a balloon, okay, so the volume displaced is equal to the volume of the element of fluid because it's totally immersed, times the gravity times the density of the fluid, not the particle. Okay. That's why what really matters is the density of the fluid you are in, not the density of the particle or the element of fluid. Okay. That's why it's easier to swim in the sea than in a swimming pool. Okay. Because you're always the same, but the element of fluid where you are immersed has a different density. Okay. So the buoyancy force that you're experiencing when you're swimming in the sea is larger than the buoyancy force that you're experiencing when you're swimming in a swimming pool. Okay, that's another. Every now and then you have to crack a joke, otherwise an hour and a half is very long, right? An hour and a half is long, so every now and then I say something stupid, so you get awake. This is an interesting few numbers. So, human body density, kilogram per liter. This is muscles, 1.1, bone at 1.5, and air is not very much. So in fresh water, in a swimming pool, okay, with air out, so you breathe out, okay. All of us will sink and we die, okay, all of us. Some of you ladies will survive, okay. Again, the same swimming pool, you breathe in, okay, so you lower your density, so the difference between the density of the fluid in the swimming pool and your own density is increasing, it's getting larger. So some of us will survive and all of the ladies will survive. Okay. So you can change so the buoyancy force is always the same because the buoyancy force is given by the density of the fluid times the volume displaced. Okay. But you can change your own density in order for the buoyancy force to win against your weight. Okay. So that's why you can breathe in and breathe out and change your own density.
So the difference between men and women is density.
There are many differences between men and women. Don't get into that conversation. Is the
density of
everything that is missing here is the relation, the proportion between muscles and bones in a man's body and women's body. So we have a different density. Usually we have a different.
Some ladies might be denser.
No.
Huh?
No.
Somewhat.
A lady taller than me must be denser than I am.
No,
Might be her weight might be larger, but not the density.
Not increased density. Density is related to the amount of
It's
ball.
divided by the volume. So if your volume is large, then it's less. So if she's large, then the volume is large, so the density is less.
But she's not that.
Don't get personal. Don't get personal. Okay, it was just a joke. So breathing in and breathing out is it's something silly. Okay, you go in the swimming pool, you breathe in and you breathe out. But it's actually something that we use every day. Okay, so this is all very simple. You know, there's static balance and the hydrostasy and the Pascal law. It's all very simple. But it's the simple things that we see and we use every day. Okay, so for example, why a boat is floating. Okay, it's just buoyancy force. Okay, and how you control your buoyancy force. For example, okay, this large container ship. Okay, the red line is the limit when you lose buoyancy and you start to sink. Okay, so this is an empty container boat. Okay, so it's filled with air. Well, it's empty. Okay, so that's why it's floating so much. Okay, and it's built that way so that it can carry weight until it starts to sink and it reaches the red line. The red line is the limit. If you keep adding weight, then buoyancy force doesn't win and you start to sink. Okay, so it's all very simple, but it's something that we use a lot every day. Another thing that is more interesting to me is this other application of buoyancy force. Okay, this is an instrument that oceanographers use to take measurements in the ocean. Okay? It's called Argo. It's called an Argo float. Argo, like the Greek word Argo. Okay? It's a float. Okay? So how the system works? Well, you will see this in Physics of the Ocean, how to measure the ocean. So how the system works is, so you take this Argo float, you pay a lot of money for this Argo float, okay? And you see how happy is that man with his $1 million Argo float, and he doesn't want to let it go because it's so expensive. And at some point you will have to let it go, okay? And you have to throw this Argo float into the ocean. So you throw this Argo float into the ocean, okay? And before throwing the Argo float into the ocean, you have to program the Argo float. The Argo float is filled with a liquid, okay? And you program the Argo float in order to acquire certain buoyancy. So this means that the Argo float will sink, as you throw it, will sink down to a certain depth while it reaches equilibrium, hydrostatic balance. Okay? dP by dz is going to be equal to minus rho g. Okay? So you reach your buoyancy level, and then you reach static conditions. Okay? So the buoyancy force that the Argo float is experiencing is balancing the weight of the Argo float. And you do that by changing the density of the liquid inside of the float. So you program the float because you want to measure temperature, salinity, oxygen, whatever, velocities at 2,500 meters. So you program the float to go down until 2,500 meters, and then it will find its buoyancy level. And then the Argo float will start drifting with the float, with the current, okay, with the fluid flow. It will start moving and going around and taking measurements. And this is the map that you see at the top is every black dot is an Argo float in the ocean. Okay, so as of what day is today? 7. So as of yesterday, today is the 7th?
Yes.
Yeah. Okay. Sorry. So as of yesterday, we had 3,964 Argo floats going around in the ocean. Okay. That's a lot of money in the float in the ocean. I was thinking of scientific. That's a lot of money. Okay. Well, it's a good point. It's a lot of money. So you could attach a flag, a national flag, to each of those dots, and you'll see that they all belong to a few countries. But the data is freely available. So if you go on the website argo.something, every data is freely available after a quality control. So maybe you don't get the data from yesterday, but you get the data from 2 weeks ago of everywhere. Okay. So the Argo float is not yours, but you get access to the data. And so you get all those Argo floats that are right now drifting in the ocean and using buoyancy and the hydrostatic balance principle and using statics. Okay, so all those simple fluid mechanics principles and a lot of electronics are into this powerful instrument for measuring the ocean, which actually changed the way we do oceanography. And so the way it works is that it goes down until a certain depth because you have set the float to reach its buoyancy at a certain level. And it measures whatever you want to measure. And after a week or 10 days, after 10 days, the Argo float is programmed to lose its buoyancy. Okay, so, and you do that, you cannot change the fluid, but you can change the pressure of the fluid, so you change the density. So you change the pressure within the fluid, inside of the float, so the density changes, and it starts, so buoyancy starts to win, and the Argo float goes up to the surface, okay, because the buoyancy force now is winning.
So does it work by heating up fluid?
By pressure. I think it's by pressure.
Pressure.
I think it's just pressure effects on the fluid.
It's impossible. Somehow to raise the temperature. It's just.
No, it's certainly not with temperature. I'm not certain, but I'm almost certain that it's pressure. So you change the pressure in the fluid, you change the density, and the instrument loses its buoyancy and goes to the surface. When it reaches the surface, you see a black antenna there, sends all the data to the satellites, and there's somebody back in some institute collecting all the data. And after the transmission is over, it recovers its original density and goes down into the ocean until reaching its buoyancy level again. And it does that for a year and a half, until the battery dies. Hopefully, this guy recovers the Argo float before the battery dies. So there's obviously a GPS, right? That's why we get the dots. So you know exactly where your Argo float is. And you can go and recover your float whenever you want. If you don't recover the float before the battery dies, then you lose it. Okay, and using the Argo, not the Argo, using the buoyancy principle, you know how much of an iceberg is submerged below the surface of the ocean. So what matters for buoyancy force is the difference between your own density and the density of the fluid. So for an iceberg is the difference between the density of sea ice and the density of seawater. Okay, so sea ice is roughly 90% the density of seawater. And so if you use the buoyancy principle, you know that if you see an iceberg, 90% is submerged. So you only see the 10% of the iceberg. Because of buoyancy. So the difference of the density tells you how much of the fluid of the volume is displaced or submerged in this case. And so from the buoyancy principle, you also get to do what do you call those common phrases that you use, like you only see the tip of the iceberg. That comes from the buoyancy principle. Okay, so now we're going to go into something a little bit more interesting. So, I guess in 15 minutes we can see the tensor notation. Okay, why are we going to use tensor notation? Why tensor notation is so much more interesting than vector notation, okay? Especially when you're working with forces and fluids. Okay? And we'll do the example of the divergence and the curl, and then look at the Gauss and the Stokes theorem that we used already. Okay, so why do we use tensors? Okay, so what is a scalar? A scalar x can be temperature or pressure, for example. You can have a vector, which can have, I have x1, x2, x3, which could be, for example, your velocity or your body force. Okay, and then you can have tensor, which is what we will use from now on. Okay, and tensor are going to be things like that. And the notation is like this. Okay. So what is a tensor? A zero, the tensor, three to 0 has one component. Okay? So everything is a tensor, just a tensor of 0 order has only one component, so it reduces to a scalar. A first order tensor has 3 components, and that's a vector. Okay. And a a second order tensor. There's 9 components, and that's, for example, a force acting on the surface. Okay? One of those shear stresses that we were talking about. So if you have, how do I do this? So if you have your element of fluid and you have shear stress, well, you have forces acting on the element of fluid, okay? Could be a normal force acting on the element of fluid, or it could be a shear stress acting on the fluid. All of those forces can be described by that tensor tau or tau ij in tensor notation. Okay? So you have all the different components of this tensor on all the different faces of the element of fluid. Okay? So why do we use tensor notation? Do, for example, a dot product. Okay, you do a product of AB. Okay. And you do A1 x1 plus A2 x2 plus A3 x3. Dot 11. Okay, and that's going to be, of course, okay, and this is simple when you have an operation like this, but when you have a vector dot product with a tensor, then it's starting to be a little bit annoying. You can do it in matrix notation, okay, and reach the same conclusion. But in tensor notation, it's much easier to do all your operations. Okay. As long as you're doing this, you don't see the difference. When you do this, you try to do it in vector notation or in matrix notation. It's quite a pain. If you do it in tensor notation, okay, you have this, or u dot tau j, or if you prefer, okay, so if you do this in vector notation, it's a pain. And you might be interested in just one component, okay? So you don't want to expand all of the different components. For example, for j equal 3, you're going to have to expand this in matrix notation, in vector notation. It's a pain. You do it in tensor notation. 1. It's much better. You just expand the component that you're interested in, which is what we're going to do. Okay. So you have a dot product, for example. You're interested in the vertical component. You just expand the vertical component. You don't have to do the whole thing. Okay. It's just an example of why you should be using tensor notation and why we will be using tensor notation. It's just the ease of using the indices of your tensors. And scalars and vectors are all tensors. They all reduce to tensors. So we're going to use when doing operations in tensor notation, we're going to use some useful tensors with very useful properties. And one of them is the Kronecker delta. Kronecker delta is my delta, ij, equal to 1, I is equal to j, and is equal to 0 if I is not equal to j. Okay? And in matrix notation, you have this. Okay, this is my Kronecker delta. And the Kronecker delta is the only isotropic tensor of second order. Right? It's very useful when you write down your equations in tensor notation because it has some nice properties. For example, this is equal to this. So basically you have the Kronecker delta, and that allows you to switch the indices. Okay, let's do it. 1, 1, 2, 2, and 3. Okay, that's my Kronecker delta on uj. So for I equal 1, what do I have? This is u1, this is 0, and this is 0. For I equal 2, this is 0, this is 2, this is 0. And for I equal 3, this is 0, this is 0, and this is 1. Okay? So this is ui. Okay, that's why the Kronecker delta is useful. Then we have another useful tensor, which is, again, an isotropic tensor, but of third order. This is, again, an isotropic tensor of third order. Okay. This is called the Levitch symbol. Okay, and so you have your epsilon I jk. Which is equal to 1 if I, j, and k are cyclic, meaning 1, 2, 3, or 2, 3, 1, or 3, 1, 2. Equal to 0 if any indices is repeated. Okay, 1, 1, 2, for example. And is equal to -1, so this is cyclic. And is equal to -1 if I, j, k is anticyclic. So 3, 2, 1, 2, 1, 3, 1, 3, 2. Okay, so this is another very useful tensor. So it's equal to 1 if the indices are cyclic, 1, 2, 3. Is equal to 0 if any of the index is repeated, 1, 1, 2, 2, 2, 1, whatever. And is equal to -1 if the indices are anticyclic. Okay, so 3, 2, 1, 3, 2, 1, or 1, 3, 2. Okay. How is that useful? That is useful because this means that ijk is equal to j, ki, and k, j, and ijk is equal to minus anticyclic, so K, J, nothing. Okay, then you can play a lot of useful ways of using the alternating tensor, or the like teach you that symbol is.
Professor.
Yeah.
I'm not good in the fact that you say it is cyclic and anti-cyclic.
So the indices have to be cyclic or anticyclic. So you have the alternating tensor epsilon ij. Okay, this is my alternating tensor. So if I have epsilon 1, 2, 3, what is this equal to?
1.
1. If I have 3, 2, 1, what is this equal to? Minus 1.
What if I was
And if you have 1, 2, 2, what is this equal to? 0. That's an isotropic tensor of third order. Same way you have your Kronecker delta of second order. 1, 1, 2, 2, 3, 3. Okay. If I is equal to j, my Kronecker delta is equal to 1. If I and j are not equal, 1, 2, 2, 3, or whatever, it's equal to 0. Okay. In a third order tensor, you have this particular tensor called the alternating tensor, okay, which is isotropic and is equal to this. So if the indices are cyclic, 1, 2, 3, 2, 3, 1, 3, 1, 2, the tensor is equal to 1. If it's anticyclic, 3, 2, 1, then it's equal to minus 1. And if indices are repeated, it's equal to 0.
Yes, probably my question would have been, why is 3 to 1 anticyclic and 3, 1, 2 cyclic?
So 1, 2, 3 is cyclic. 3, 2, 1 is anticyclic. Is that answer your question?
And 3, 1, 2?
And what?
3, 1, 2.
3, 1, 2 is cyclic. 1, 2, 3, 1, 2, 3. 2, 3, 1 is cyclic. 3, 1, 2 is cyclic. So ways of writing things in tensor notation. Oh, there's that now. Any other questions? I don't want to start something that I cannot finish. Clear? Yeah. Just going in one direction or the opposite direction on the indices. So IJK, IJK, IJK. If you're going in one direction, you go cyclic. If you go in the opposite direction, you call it
We can write I, J, K, and by moving around clockwise, we can put some messages.
I think circle.
Oh,
Yeah.
J,
I think
yeah, just moving
circle.
these are the
clockwise. Clockwise.
So if you go like
Yeah,
this.
yeah. This I, J, K. Okay, let's see zero.
Whichever way you can figure it out in your head.
Yeah.
Swiss convention.
Yeah.
That's what it might be, it's like be a runner.
Yeah. Crossword, okay.
Scusa, mi sono dimenticato una mattina.
E Gabriele?
Ciao.
Tu
dove vieni? Perché
io matematica. Infatti adesso... perché sono sempre santo, che è il mio supervisor, e tu di siccome io faccio ricerca adesso, ho fatto studiare soluzioni deboli, spazi di sopra, eccetera. Dovevamo scegliere un po' di corsi e mi ha detto il livello di matematica non sarà alto, però almeno l'aspetto fisico che io zero, anzi meno di zero, anche perché quando abbiamo fatto l'esame di ammissione mi ha chiesto ma a livello fisico, guarda, a livello fisico non so. Se vuole può dire a qualcun altro, ma a me...
Vabbè, noi iniziamo da 2 corso.
So the information we are getting is very expensive and we are taking
Però adesso ti do di nuovo il sito. Le nuove lezioni le faccio io, che sono